Hello, everyone. Thank you for tuning into my talk. My name is Trent Thomas. I'm a PhD student at the University of Washington in Seattle, and I will be discussing a project that I've been working on with Dr. Renyu Hu at Jet Propulsion Laboratory, a nitrogen-rich atmosphere on ancient Mars indicated by isotopic evolution. So I'll begin by giving some background and motivating the problem that we investigated. It's no secret that there's evidence for water on ancient Mars. The morphology shows evidence of precipitation in the form of valleys, lakes, and deltas, and the mineralogy shows alteration products that only form in the presence of water. So we wonder what type of atmosphere on ancient Mars would be consistent with this evidence and allow sustained liquid water on the surface. In this table, you see that the modern Earth has a thick atmosphere, allowing temperatures high enough for liquid water, of course. But present-day Mars has a much thinner atmosphere that does not allow these temperatures. We expect the ancient Martian atmosphere was much thicker than it is now, and it may have been comparable to the modern Earth's atmosphere. So it's a common thought that CO2 would be dominant in this proposed ancient atmosphere, meaning it would be responsible for most of the greenhouse effect. But it has been shown that CO2 alone cannot warm Mars enough to allow liquid water. So we turn to nitrogen in this study and investigate its role in the ancient atmosphere. We begin with N2 at ancient times, these times defined as 3.8 billion years ago, to avoid complications from the late heavy bombardment. We don't know the partial pressure of N2 at this time, and in fact, this is exactly what we are looking to constrain. But we do know the delta N15 value at this time, which is a measurement of the isotopic composition of atmospheric nitrogen. 3.8 billion years have passed since then, and today we know the present conditions of Mars. In this study, we modeled the sources and sinks of atmospheric nitrogen over this evolution, represented by the red and green arrows in this figure. Each source or sink has a unique impact on PN2 and delta N, which allows us to use those measurements as constraints on the evolution. Let's take a closer look at these sources and sinks. Here's an overview of what our model includes. We incorporate solar activity models, MAVEN data and MAVEN validated models, Mars interior models, surface analysis, and measurements of crustal nitrate deposits, all of which extend back over the last 4 billion years. After investigation, we identified key uncertainties in these mechanisms, captured by these 7 parameters. Uncertainty in the exobase altitude and temperature has an impact on fractionation from escape to space. The multiplier and power law exponent of photochemical loss captures the uncertainty in the overall process of that, and the same goes for the multiplier of sputtering and the multiplier of volcanic outgassing. And there's also uncertainty in how deep into the crust nitrate deposits actually extend. Finally, the most important parameter, the initial pressure of N2 at ancient times. With the knowledge of our model construction in hand, we can now discuss how varying these parameters results in different evolutionary scenarios. The first result we find is a bifurcation in evolutionary pathways. In this figure, the y-axis shows the pressure of N2, and the x-axis shows how it evolves with time moving towards the right. Each dotted line is a simulated evolution of PN2, and the only difference between each line is the initial pressure, so where it starts over here. Previously, it was thought that N2 had evolved in a steady state. In this case, a wide range of initial pressures will all converge to the same evolutionary track, so all of the solutions underneath this thick black line. In this case, you cannot gain information about the ancient pressure of N2. However, we have discovered that if you raise the initial pressure over a certain threshold, that black line, the evolution will become unique, and crucially, you can now gain information about the ancient pressure. We call these dynamical tracks, and we have found that they are able to explain the present-day conditions of N2, both the pressure and the delta. There's one thing you take away from this talk, it's that these new solutions allow you to gain information about the ancient N2. With this in mind, we want to find out how these different tracks relate to the parameter space we're exploring. To do this, we employ the statistical search method of Markov chain Monte Carlos, with the goal of finding parameter combinations that recreate Mars's current conditions. But where in the space should we explore? Well, the answer is these 2 ranges, the constrained range where the key multipliers are kept close to our best estimates, and the unconstrained range where they are allowed to vary essentially anywhere. And in both cases, PN2 is essentially unrestricted. On this slide, you're seeing 100 randomly sampled solutions from each parameter space. The left column here shows the evolution of PN2 moving to the right with time, like in the previous figure. In the constrained space up here, all of these solutions are either in the dynamical track or have a very late convergence to the steady state. whereas in the unconstrained space at the bottom, these solutions are all converging very quickly to a steady state. And this leads us to believe that the dynamical solution is the preferred track of the constrained parameter space. Additionally, when looking at the right column, which shows the delta N15 evolutions, we can predict a measurement that will help determine the true path that N2 followed. Because the two solution types differ so greatly in the middle of their evolution, a measurement of delta N15 from around 2 GA, somewhere in the middle here, it may illuminate the actual correct pathway. Finally, here are the posterior distributions from the two MCMC parameter searches. The leftmost figure is the ancient pressure, and the three figures on the right represent the key evolutionary mechanisms. Looking in the unconstrained space down here, these steady-state solutions do not preserve the memory of the ancient pressure, and this distribution contains very little information. On the other hand, solutions within the constrained space up here allow us to gain information about the ancient pressure. Specifically, that it has a median value of 250 millibars with a 95% confidence interval of 20 to 500 millibars. To conclude, here's an overview of our investigation. First, our model reveals the family of dynamical track solutions in contrast to the previously known steady states. From this, our MCMC indicates that the dynamical tracks are more likely when parameters are close to our best estimates. If our best estimates are sufficiently accurate, then PN2 likely evolved on a dynamical track. And with the knowledge that we can reconstruct the initial pressure from these tracks, we conclude that Mars likely had an N2-rich atmosphere at 3.8 GA. Looking forward, it is known that N2 can substantially enhance the greenhouse effect of a CO2 atmosphere. Thus, our findings may provide a new pathway for explaining the geologic records that suggest persisting liquid water conditions on ancient Mars. This concludes my talk. Thank you for your time.